Recording. Okay, so today we're going to be talking about chapter 12. Um, Chapter 12 is about something cool, right? So it's about partitions and relations and equivalence relations. The whole equality problem comes back every time, just in a different form. Um, okay, so first of all, we're going to pause talking about groups. I'm going to go back to talking about sets. And if you have a jar of coins and you separate into piles of pennies, nickels, dimes, and quarters, and half dollars, that process is called partitioning of the set of coins. Each separate pile is called a class of the partition. The jar full of the coins has been partitioned into 5 classes. Um, so this is essentially like a separation, right? So you are dividing. You have a criteria, which we're going to talk more about it later, and then you divide your set into subsets, uh, and they are calling classes. But these subsets they have properties, so that's very important. To partition a set A is to separate the elements of A into non-empty sets. So that's the first constraint, and they need to be disjoint. That's also another constraint. So they have no elements in common. And then we go to this definition here. A partition of a set A is a family of non-empty subsets of A which are mutually disjoint and whose union is all of A. So you can always get A back by doing a union on all the partitions. And then we can number the partitions using indices. And you could think that the indices are names, but that's not necessarily true because it may be inconvenient to insist that each class must be named once and only once. So it is simpler to allow repetition of indexing whenever convenience dictates. For example, the partition illustrated previously might also be represented like this, where A1 is the same as the class A5 and A2 is the same in A6, and A3 is the same as A7. You could do that, but then that implies that any two distinct classes of a partition are disjoint. This is the same as saying that if these two classes are not disjoint, they must be equal. So you either are exactly different, like necessarily different, or you are the same. The other condition for the classes of a partition of A is that the union must be equal to A. That is the same that every element of A lies in one of the classes. True. And then we go to this other definition. If any two classes say AI and AJ have a common element, then AI is equal to AJ. Every element of A lies in one of the classes. Then we have examples, which in particular we see that we have a relation example. So relation on a set A is any statement which is either true or false for each ordered pair of elements of A. Examples of relations on appropriate sets are equality, less than, parallel to, offspring of, and so on. An especially important kind of relation on sets is the equivalence relation. Such a relation will usually be represented by the tilde symbol, and we say that x is equivalent to y, and the equivalence relation respects three properties. Which, as far as I remember, this is the same set of properties as partial ordering, isn't it? Or am I crazy?
Partial ordering is not symmetric.
Really? I thought it was. I thought it was. Well, it's the opposite. It's anti-symmetric. I got confused. Uh, yeah. So reflexivity. So if that is x is equivalent to x for every x in A. Symmetric. That is to say that x is equivalent to y, then y is equivalent to x. And transitive. x is equivalent to y and y is equivalent to z, then x is equivalent to z. Equality holds for that, of course. Um, Equivalence relations also arise in a natural way out of partitions. We call two elements equivalent if they are members of the same class. It is easy to see that this relation tilde is an equivalence relation on A. Indeed, x is equivalent to x because x is in the same class as x. Um, if x and y are in the same class, then the opposite is also true. And finally, the transitivity also holds. Thus, tilde is an equivalence relation on A and is called the equivalence relation determined by the partition. Um, so there is a term for this. It's fungibility. Is that what I'm looking for?
Uh, Maybe.
It's in the sense of money, then I believe it is
In
what
economics
you're
and
looking
law,
for.
fungibility is the property of something whose individual units are considered fundamentally interchangeable with each other. So my understanding is that if you are equivalent in money terms, you are fungible.
That is correct.
Yeah. Um, Let tilde be an equivalence relation on X and X an element of A, relation of A and X. And the set of all the elements equivalent to X is called the equivalence class of X and is denoted by this. Then we have the property. If X is equivalent to Y, then all the equivalent class of X is the same as the equivalent class of Y. If two elements are equivalent, they have the same equivalent class. The proof of this lemma is fairly obvious because if they are equivalent, then the elements equivalent to X are the same as the elements equivalent to Y. Um, then it talks about examples with coins again. And it says that if two coins are equivalent, then they are in the same pile, because the pile in this case would be the class. And we're talking about equivalent classes equality anyway. Then we have the theorem. If tilde is an equivalence relation on A, the family of all the equivalent classes, that is, this is a partition of A. To me, this is also fairly intuitive. So it states that if tilde is an equivalence relation on A, and we sort the elements of A into distinct classes by placing each element with the elements equivalent to it, we get a partition of A. Which means that it's disjoint, and if they have a common element, they are in fact the same. To prove it, we observe first that each equivalent class is a non-empty subset of A, because because of the reflexivity, right? Next, we need to show that any two distinct classes are disjoint, or that if two classes equivalents of X and equivalents of Y have a common element, they are equal. Well, if they have a common element, then this is going to be true. And by symmetrical transitive laws, we say that X should be equal to Y. Thus, their equivalent classes should be the same. So we just proved that if they have a common element, essentially the common element pollutes the thing and make them the same. As soon as you have one, you're done. Finally, we must show that every element of A lies in some equivalence class. This is true because at least we know at least X is part of the equivalent class of X, at least that. Thus, the family of the equivalent classes is a partition of A. When tilde is an equivalent relation of A and A is partitioned to its equivalent classes, we call that this partition the partition determined by the equivalence relation tilde. And then it goes into a conversation about you can come from one concept and lead to the other and vice versa. So you have the concept of a partition and the concept of equivalence relation. And if you pick the correct pieces throughout the construction of each concept, you end up with the other concept, which is fairly obvious, right? Because if you're trying to make a partition, and it just so happens that your partition criteria to say if they should be in the same pile make there's any notion of equivalence using reflexivity, transitivity, and being symmetric, then you're going to end up with an equivalence relation and equivalence classes and stuff. And the other way also works. If you start with the equivalence relation, you end up with partitions.
You could say that there's an equivalence relation between equivalence relations and partitions.
Sure. My final comment is in order. So in general, there are many ways of partitioning a given set A. Each partition determines and is determined by exactly one specific equivalence relation on A. Thus, if A is a set of 3 elements, there are 5 ways of partitioning A, as indicated by the accompanying illustration. And this seems like an explosion problem, right? Because there's many ways, as you have more elements, of choosing one specific equivalence relation to make that happen. So under each partition is written the equivalence relation determined by the partition. Um, yeah. Once again, each partition of A determines and is determined by exactly one equivalence relation on A. So each one of these 5 um, pictures, and the equivalence relation is determined above. Um, so yeah, uh, that figures. It's more of an isomorphism than equivalence relation, but anyway, I guess. Um, yeah, the way that this book states partition and equivalence relation, you kind of end up with this. Oh, one can very easily lead to the other if you choose the pieces correctly. Because it's still, you still have to create a criteria, right? So in the case of the poker chips, they chose the color, and that ended up creating equivalent classes. Equivalence classes, I should say. Um, you guys should, okay, we finished the chapter. We can go to the exercise, but you can state what you're writing via voice, money. That's fine.
Well, they will say that it's more of an isomorphism than an equivalence relation, but an isomorphism is an equivalence relation. It satisfies, well, if you consider it together with the inverse, right? The full isomorphism, not just one
Ah,
direction.
okay. I was about to do a gotcha on you. You have to consider the inverse. So Marin was talking about that if you pick an isomorphism and its inverse, then you apply. It has all of these properties, right? Because something is isomorphic to the same something. With the inverse, you have the symmetric portion, and transitivity
It's just composition.
is just composition. Yeah, it's just composition. Yeah, yeah. Equivalence relations. Go figure. Go figure. Um,
Kind of funny that we're taking this detour in the middle of the book.
I don't think it's a detour really. Well, it's a detour in the sense that it kind of feels disconnected. But my understanding is that we're gonna glue that to the idea of groups later, and then like fusion time. Um, that's my expectation, right? Because we've seen like everything connects to groups anyway, and there are exercises about groups in this chapter. We're gonna go through that. But my understanding is that our next step is to essentially connect groups more intimately with the idea of partitions. and equivalence relations and things like that. The only thing that I'm kind of it still hasn't clicked for me is that how does this relates with like usually when we talk about relations we're talking about relational databases, right? And is the equivalence relation important for us in that context as well, or am I just tripping?
Well, it is one relation, or rather, there are many relations that can satisfy the property of being an equivalence relation. The most obvious one is equality, and equality is, well, you need equality to define joins, right? So there you go.
Oh yes, but it seems to me that equivalence relation is more like a superset of equality in this case. It's trying to be more general than equality. That's why we can have more than one that satisfies it. And I wonder if there's anything deeper about trying to be a superset of equality. Anyway, um, okay, so exercise times. We have 44 minutes. Exercises of A. Does anybody want to talk about it?
A lot of this section relates very deeply to modular arithmetic.
Again. Yes. Well, it's because for example, the A1, right? This is precisely this is forcing us to figure out that actually when you wrap around, you go back to from 0 to 4. So like that's why that works.
Yeah, this is relating. Well, this is relating like arithmetic mod 5, the congruences as forming a partition of the integers, right?
Yeah, and it's fairly intuitive that if you have all the integers and you divide them into the remainders from 0 to 4 of a particular of 5 of dividing by 5, you're gonna have all the integers eventually because it wraps around. So I wouldn't say it's surprising because I'm already expecting modulo to be mentioned anyway. So there's that. There's that. Anyway, any other A exercise that you guys want to highlight? Actually, I do have a question about A4. So when they say all the integers whose units digit, what are we talking about? In decimal notation, is it the left hand side of the comma?
The units is the least significant digit, so
That's
Okay,
essentially
so
modulo 10,
it's
by the
essentially
way.
modulo 10, yes.
oh, okay, no, so the units digit is just the unit as like when we were like in I don't know, in very like okay preschooler level, the unit is the least significant one. Yeah, this is modulo 10. Anyway, I was kind of confused on what they meant by units digit, but it's the simplest
If
possible answer.
Most of those relations are modular relations in some way.
um, A5 is modulo related even actually. It's rational numbers modulo 1, which is very unusual but very fun.
Wait, I don't get it. So for any rational number x, we can write that where q is an integer. Sure. Call n divided by m the fractional part of x. For each rational there, let AR be x, that is in ration the fractional part of x is equal to r. Prove that that is a partition of rationals. So you said rationals modulo 1,
Yep.
and what is modulo 1 in rationals actually?
Uh, well,
It's
you're
the fractional part, essentially.
it's the fractional part. Yeah, it's basically
That makes sense.
Yeah, basically every integer is divisible by 1, but if you try to do Euclidean division, I mean, in that sense, right?
Yeah.
But if you try to do that with rationals, actually there are a lot of rationals that are not divisible in the Euclidean division sense by the number 1. So you get all kinds of. Well, basically, you can get
What? Give me an example of a rational number that is not divisible by one.
a half,
Sure.
like
Sure.
yeah, basically any rational number which is not an integer
Yeah.
will have a remainder if you do an integer division with 1.
Yeah. Sure. Yeah. I haven't thought of that in those terms, but again, I'm not a rational freak, so that's I didn't figure that one out. Uh, cool. Okay. Any other exercise on A? Can we move to B?
A6 was almost interesting, but it isn't because they used reals instead of using naturals. It's kind of sad actually.
I don't see how that makes it less interesting, but okay.
It's less interesting because if they had used the naturals instead of the reals, this would have been an example of how to define integers in terms of naturals.
Ah, I see. It's because if it was naturals, then you would have derived the negatives in this thing, right?
Yeah, because one way you can define it, it's not
I
the
see.
most computationally efficient way, but it's one way is to say, okay, an integer is a pair of natural numbers where logically the right hand side of the pair is considered negative.
But are you gonna fix the? You said the right hand side, but this is already doing the operation of the subtraction. So you would say, it's fine. No, I understand what you said. It would be more fun. Okay, that's fair. Okay, B. Examples of equivalence relations. Prove that each of the following is an equivalence relation on an indicated set. And then describe the partition associated with the equivalence relation. So is this all the positive integers?
In integers, this is basically making each integer equivalent to its negation.
I was about to say that this is making an integer its positive version. Am I being simplifying things?
Well, kinda, because if you say, because like, um, if you take the absolute value of a negative and of a positive, it is possible that you end up with the same result, right?
Oh yes, because you are mapping both to the same positive.
Yeah, so basically it's saying, okay, each number is equivalent to its negation in addition to being equivalent to itself if you define equivalence in terms of,
But
well,
but
how it is
if
defined
but
here.
if m is a positive integer, you're not going to the negation.
The point is that it would be indistinguishable from the negation under this equivalence relation because
Exactly. No, I agree with that statement. But to me, that statement holds not because you are mapping everybody to its negation, but because you're mapping everybody to its positive version. Because the negation of a positive, what is the negation of a positive integer?
well,
It's the negative, no?
it well it is. But the point is, I didn't say you were mapping to its negation. I'm saying you are making it equivalent to its negation in addition to being
Okay,
equivalent to
okay, okay.
itself.
That matters. That difference. Okay, we are saying the same thing. Div.
No, I wasn't really going to add anything,
Okay.
I guess.
Um. Okay. Any exercising B that you guys want to talk about? And just a thing. I think that the most interesting part of this exercise is to describe the partition associated because proving that it is equivalence relation is just following the steps, right? This is a recipe. This is a mechanically doable thing that is like less fun, let's say. But I think that describing the partition associated is more fun.
I like B9 actually.
B9. This is there is a name for this. This is distance, isn't it? But this is without the square root.
This is a quadrant, yes, which is also called the square of the distance for some reason.
No, it's because the most there are many ways to calculate distance in metric spaces and stuff, but one of the most um, common ones that people know, the common factor is just people knowing. I'm not saying it's the best way. It is the square root of the sum of the squares.
Yes, I'm aware, and I think that's terrible because the square roots can force you out of the rational numbers.
Well, I like that one because it's the closest one to being that you can experiment with. The the square of the distance is something that you cannot measure really. You're gonna have to do the square of the measurement. But I understand your concern. I'm gonna say it's understandable.
Actually, there's a different argument that I could make that doesn't even go into whether you believe in real numbers or not, which is actually the square of the distance is physically more significant than the distance itself.
What are you calling significant? What is the definition of that word in that sentence?
It's because there are lots of physics equations. There's even a name for this. It's called an inverse square law, where you have a quantity which is derived by dividing by the square of the distance. Like this is used for gravitation, electromagnetic
Yeah,
force,
yeah, yeah.
all kinds of things actually. And I found it weird that it was the square of the distance, and then I found the idea of okay, rational arithmetic. Let's not do square roots, and then oh, actually the square of the distance is significant mathematically, not just physically. So I don't know. I think
I
that's
don't
kind of
get it.
neat.
I haven't gotten the meaning of significance still. What are we
Uh,
calling significant? Because here's the thing. If everybody is doing square of the distance, it doesn't matter, really.
but it does because you are not leaving
No, 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 no,
the
no, no.
realm of
No,
rationals
no, I mean,
necessarily.
no, no, I understand that. And if that's what you mean by significant, that's okay. I'm saying that if I'm doing all my calculations with the square of the distance in my distance function, and I do that consistently, everything is going to be fine. A vector will be just as close as it was before in comparison to a third vector
Um,
if we use the square of the distance. It's fine.
Well, actually, it changes quite a few things in regards to the equations that you derive out of it. Um,
Ah, the equations. So you're talking about the formulas then.
yes, because, well, first of all, if you're avoiding square roots and everything is squared relative to where you would be used to using, right?
Yeah, sure.
You end up getting some factors of 4 in a few places that you're not used to seeing,
Yes, that's
which is
true.
one difference. But also another difference is that because this is a square, this is never going to be, or it could be 0, but it's never going to be strictly negative. It's always going to be positive. So the direction doesn't matter actually.
Is that what significant means then?
Not really. When I said significant, I was talking more in regards to it's actually rare in physics to see a plane distance compared to seeing a squared of the distance.
Ah, you mean about being like when you derive the stuff, you see more square. Like if we not if we don't force it, we're gonna naturally lead more times, more often, to the square of the distance than the distance.
Yeah.
Makes total sense because I've seen um, the those and in college, and that is true. Usually, you see more the square of the distance, and in particular, in my opinion, not only because of the whole metaphysical argument, but also because of a precision slash computer limitation argument, which is if I'm doing distances on vectors because I'm doing some k neighbors stuff, so like I'm doing a very simple AI model, I did that on distances when I did it in Python in 2018. But if I have to redo that, not only I wouldn't be using Python for it, but I would also not be using distance for it. I would be using the square root of distance. uh, because when I
Because
implemented that, it took me years to figure out that, wait, a vector is not closer or farther away than another vector if I use the square of the distance, if I use that math for all of my comparisons. It doesn't matter.
yeah, even if you are willing to do the square root, it turns out doing it once is more precise than doing it all over the place.
No, yes, not only that, but I would not even do that. I wouldn't even bother. I would just say, okay, this vector is closer to this vector in regards to the square of the distance, and that's it. I like I'm gonna compare it with a v3 vector using the same criteria, so it doesn't matter. Anyway, C. Okay, and no more comments about B. Can we go? Like I said, this is very just like follow the properties, and they're gonna be able to prove all those things. And out of
B10
the
is basically just the rationals.
rationals, um, yes, yeah, I think the most cool thing is just identifying the partitions. All of these exercises. What do you get from it? That's the coolest part. Okay, so C. So I read the solution for this one, and it's essentially okay. And before I say anything, so does anybody want to talk about C exercises at all?
I'm just going to comment that C2 is the same
All the
relation
spheres.
as B9. Is the equivalence over the magnitude of the vector.
You said C2 and B9?
Yes.
Yeah, sure. That is true. But I don't know. To me, this is clearly circles, right? These are circles.
Yeah, that forms a circle.
Yeah,
I should
this
graph it
one
out.
also kind of does, but this is more doing a poke on the square of the distance, in my opinion. This one is for the circles. This one, as I said, I saw the answer, but it's kind of like fairly fine to know. These are all the curves with slope 2. Um, this is also probably some sort of curve. Not a curve, a line, right?
Uh,
Oh no, this is all
It
the
forms a V shape because you're taking the
V.
absolute of x.
yeah, because it's going
Yes, that is true.
to
These are all the
yeah,
V's.
it's going to change direction as soon as you hit zero, basically.
And okay, I should define what I mean for the recording. When I'm saying, oh, these are all, we're talking about the classes, right? So before you're doing a pile of nickels, and that was the class, and that's kind of the gotcha moment. That's the conclusion of the intuition process of what this means. What I am stating, and Teo and Manning already got it, we are talking about what is the class that is constructed out of these things. And here are all the lines with slope true, all the circles, and this is all the V's, as Tevo said. And the reason that we do that is because this is, like I said, everybody's here for mostly for the intuition, and this is the intuition out of this thing. This is a different way of encoding a class in math instead of doing in English. You say this thing. Okay, so now we have to prove it's an equivalence relation and describe it geometrically and giving the corresponding partition. So what is this one?
Where a, b are greater than zero. Uh, hmm. This thing is a bit similar to um, B9 and C2, but it's
Are these
adding some
ellipses?
additional. Yeah, it's adding some additional constant factors to each side.
Yeah, I think these are ellipses because circles they kind of shape like this.
Yeah, A and B are equal to 1 in that case, right?
Yeah, and this thing is more like an ellipse. So this is like uh there is a Kepler thing about it, isn't it? About the orbits of the planets and things. That uses this thing. This is like very very deep down in my memory lane of like high school stuff. But I'm satisfied with this. These are ellipses for sure. And then in this one, we have x plus y equals to u plus v. These are all the lines. Is that it?
Mm,
Because if you see this as a graph, a is always 1, so the slope is 1, and this is the shift, the horizontal shift, right?
not really. If you interpret those pairs as points, this is basically saying 2 points are equivalent if adding up each component gives the same number.
Yeah, but what is that?
Mm, that is, let's see.
Is there a magnitude thing that uses just this instead of the squares?
There isn't, no.
I think that's just downward lines, yes.
These are lines, isn't it?
I think those are lines. Like if you write them out as a relation and move the y to one side, you end up with a negative x. R minus x, essentially.
Yes. Okay, I'm not completely sure about it, but my first intuition is that those are lines.
Yeah, I think Dev was right. Those are lines going
Negative,
down.
right? Yeah, negative slope, right?
Yeah.
Yeah. Okay, we should explain why, because maybe people are saying well, maybe somebody's watching this later. The reason why is because if you fit this into a y equals x, so f of x equals x, the x needs to go to the other side of the equals. So you can imagine that this is x plus y equals 0, and then y is going to be equals to minus x, so the slope is minus 1. So these are all the lines that have negative 1 slope. Actually, yeah. Actually, these are all the lines.
You're basically saying 2 points are equal if they are in the same line with -1 slope.
Yeah, yeah. 2 points are equal if they are on the same negative 1 slope. Yeah, but this is a single line, so these are not all the lines. These are all the points on that line, right?
Uh, well, no, because you can have arbitrary values for x and y, right?
Okay, no, so these are all the negative lines. Okay, I got it. What about the last one? C6.
That I believe is parabolas facing up.
Parabolas, yes. So these are all of them, right? All the parabolas, because this is negative y. So these are all the parabolas facing up.
I believe that is so.
For the same argument as the negative lines. Cool. So D. Okay, then it comes the thing that I mentioned before. We have equivalence, relations, and groups. And I'm not gonna lie, I had a hard time on these. In particular, because if H is a subgroup of G, and we kind of remember what that means, we say that A is equivalent to B if and only if A, B inverse is in H. How do you even start this one?
Uh, well, first of all, you need to prove that, like, if you do the three things, like, if it's reflexive, transitive, and symmetric, right?
Yes.
The symmetric part is actually pretty interesting because you can get it for free based on the fact that this is a group, so the inverse element will be there, right? And it turns out that if you flip A and B in the relation, you happen to get um, precisely the inverse of A B inverse, which is B and A inverse.
Wait, repeat the last part?
Like you can prove that this is symmetric because the inverse of a product involving, well, the inverse of a product is the inverse of the element in reverse order, right? We saw
Yes,
this
so AB
way back.
inverse is the same as BA inverse on everything.
Yeah, if you put the inverse on everything, what you get is
BA.
B followed by A inverse. And that's exactly what you get when you do B equivalent to A. Like if you flip the parameters of
Ah,
the
just remind me, is the when you do the trick with using the theorem, is the inverse on parentheses or is only on the A?
um,
Maybe I should write it, but well, I don't have the setup here. I haven't done it. I don't
well,
remember.
if you put the entire thing in parentheses and do an inverse on the entire thing, you're basically saying, okay, I have this product which involves an inverse. I want the inverse of the entire product, basically. And that needs to be inside of H because otherwise H would not be a subgroup because
Yeah, no, no.
uh,
That part follows, but I just want to understand if the this is equal to BA parentheses inverse or it isn't.
no, it isn't.
So it's BA and
And the inverse is only on the A, yeah.
oh, I see. I see. The inverse is only on the A. Okay, so it's been a while. I should have revised that. But there are things that we've seen before. For example, there was an exercise particularly about this one, right? About having the thing and the inverse of the thing, and they were squashing like sandwich style on the something else.
Yeah, that's conjugation, if I recall right.
Yeah, there's that. Well, like I said, I had a very hard time on this one. Is there any comments, anything you guys want to highlight on D?
Mm, not really.
Devo?
Not really, I guess.
Okay. Um, yeah, sure. Okay, then E. E, I do have a comment. I think I have a comment on B4, E4. But let's go over some of them. So first, it's saying that we have indices, and that is a partition and things. We have partitions. We have partitions of A, partitions of B. Then it wants us to prove that if the
I think there's
partition,
a typo in that set, but okay.
which one, the B or the A?
Like prove
No, there
that
is
blah
a
blah
there
blah.
is this one.
Yeah,
There is a typo here for sure because this is missing the I on A.
yeah, and that comma after the product should be a colon, I think.
Yes.
The comma should be. Oh, no, yes, the second comma. The
Uh,
first comma should be an I.
yes. The first comma should be an I. So it wants us to prove that that's a partition of the Cartesian product, right? So my understanding this is kind of like fairly obvious. Like I'm gonna use the same words as the book. He said fairly obvious before. I'm just using that. He said it. Like I'm learning from the teacher. Come on. Uh, so I don't think we need any comments about that. So then we go to A2. So let that be the equivalence relation corresponding to the above partition of A, and let tilde j be the, I said tilde 1 is tilde I, and let tilde j be the equivalence relation corresponding to the partition of B. Describe the equivalence relation corresponding to the above partition AB.
You would have to basically describe how to derive this composite equivalence relation from the parts, I'm guessing, is the intent here. Which is basically like uh, what was it called? A bimap? A dimap
Bimap?
from category theory, where it's like you have two pairs of elements and you have a function that takes, well, I have two functions. One that takes two elements of the left type and one that takes
Yeah, it is
an
bimap.
element of the right type. Yeah. And then you have to basically say, okay, the pair is equivalent in this composite equivalence if the elements are pointwise equivalent using the respective relations.
Which is a perfect kind of fit. What you said fits perfect with E3, right? Because this is extensional equality. In your case, F will be bimap, and A
A
and
is
B will
equivalent
be
to
pairs.
uh, kinda, but not really, because in the case of E2, you would have to do the pairwise comparison using the equivalence relation, and then you have to do a conjunction in both of them.
In both of them,
Like,
what?
sorry,
You said you need to do conjunction on both of them. Which them? The
like
both pairs?
you have you have the two pairs, right? So
Yes.
you have to you have to check the equivalence of the left elements, and that's the conjunction. You have to check the equivalence of the right elements.
Yes. Yes. Yeah, but that's essentially saying if and only if bimap equals to bimap, isn't it?
Mm, kinda, I
Bimap
guess.
kind of does what you said automatically of the conjunction.
Well, no, the bimap would just take the two pairs and the two relations and give you well, if you represent the relation as a function returning boolean,
Yeah.
it would give you a pair of booleans, and after you get the pair of booleans, you just have to check that they are both true, basically.
No, no, no. Let me be more specific. Imagine that f in here would be bimap to the I to the j, right? And the element is a pair is a pair constructed out of the Cartesian product AB. Then you have to qualify to make sure that you are doing equality between two different pairs, right? So there needs to be an index and stuff, but I'm kind of skipping those details. You say they are equivalents if bimap to the I to the j with the point A is equal to bimap to the I to the j of a point B.
Not really. You would be bimapping the equivalence relation, but that's a function of two arguments, right? If you interpret it that way.
No, I'm sending a point to it, so it's I have two things.
But you see, the two functions that you have are for each component of the point, which may be different types.
Could you repeat that?
Like, if you have a pair of A and B may be different types, right?
Yes.
So if you have a function that takes two A's and returns a Boolean, and another that takes two B's and returns a Boolean, you can just bimap over the pair.
Ah, I see what you're saying. I see what you're saying. I cannot just do equality. I need to pass the other point to like make the couple and then do conjunction on them.
Yeah.
Jeff, did you follow all of that? Because that like Mario and I were kind of talking in a particular dialect here. Did you follow that, or do you want me to explain it better?
Could you summarize it, please?
Sure. Okay, so there is an operation that called bimap. Okay, and that operation allows you to grab two like grab functors that are glued
It's like
together.
map distributed over tuples, if I got it correctly.
Yes, but that's because you can make the tuple a functor.
A bifunctor
Yes.
with two type variables, basically.
Yeah, so you have the tuple. Imagine that you have the tuple, and you are mapping the two elements of the tuple to something else. Okay, so far. The reason that this Marinho mentioned bimap is because bimap allows you to pass two functions for the mapping, which in this case, it kind of intuitively at first, because it doesn't really work like that way, you want to pass those two things as the functions for bimap. You see? The problem is
That
that you are the bimap is going to map at the A. So imagine a tuple AB, and you're going to a tuple CD. The first function maps an A to a C and a B to a D, and the second function B to a D. The problem is that equivalence relations don't work that way because they need to receive two A's for comparison and two B's for comparison. And that's why I got confused. You see?
but then your A's and B's on the equivalence relation are the tuples, and you
Um,
define the equivalence relation as a bimap
well, we are
in
trying to
theory.
define that. That's kind of the exercise. So I was trying to define this equivalence relation of the pair in terms of bimaps. But Marinho said you cannot really do that because the the functions I tilde I and tilde j, they don't take each member, like they map one portion of the point to something else. So that would give you a boolean after bimapping.
Yeah, you would need some kind of bi-applicative
Yeah.
to tie the two things together.
And then you need to do conjunction on them because you need to see if both comparisons worked. And that's not how bimap works because bimap receives one point and we need to send 2 points to it.
Yeah, it's basically a bi-map bi-reduce that we're doing.
Yeah. I hope that helped. We can talk more about it later, but I hope that helped. Uh, Devo, are you there? Are you alive?
I think I am imagining a different operation then.
Yeah, that exactly. No, it is a different operation. Bimap is not going to really cut it for this. Um, because you're going to
Here's
need
a
some applicative.
here's
Anyway,
a type signature to help you out, Tevo. Let me just finish typing.
and I apologize that we went into this tangent, but well,
That
uh,
is actually what I had in mind. So I don't get why we can't use that.
it's because you need to send bimap takes 1 point.
Oh, okay. That
Yes, you got it. Bimap takes 1 point and converts 1 point, but we don't have 1 point. We have two. So if you
I
bimap it, you're gonna have booleans after.
Well, if you bi-map the first point, you're gonna have a pair of functions which you then have
that
to
take the
apply
second
to
point.
the second pair to
Yes,
get a
Yeah,
pair of
yes.
booleans.
makes
See?
sense.
And then you have to
So you need
um,
a bimap and a biapplicative, and
yeah, and then you have
okay.
to uh, is it a bifold in that case? But the two parameters have different types potentially, so I don't know if that's the right.
I think we could just pull this off with a biapplicative, but I don't know if that's really a thing because I
The
we don't
problem
I
with the biapplicative is that you don't have a way to make the two components of the pair interact, which you kind of need, right? You need to check if they are both true at the end.
Yeah, no, but for that you could use a function called on, which allows you to collapse. On is essentially a very primitive version of fold, if you want to think about it. But it applies. We can get into those details later. But I think Tevo got the problem. If you use by map, you're gonna have a couple of functions later, and you have to apply the second point to it, and then you have to converge these booleans after to see if it's actually equivalence or not.
Yeah, that makes sense.
Cool. I 100% think most people dropped the car if they are watching this thing. Dropped from the car. But I apologize, but this is how we work. We read things and we want to correlate what we read previously to what we're reading now and making correlations between them to solidify the intuition. And I apologize, but well, we have 31 videos reading category 3 for programmer's book.
Yeah, if for the sake of if any of the future watchers of this video get confused, go watch the other series first.
Yeah, it's not 31 videos, it's 31 chapters. There are less videos than that, hopefully. Anyway, so going back to the exercise, because I still want to talk about the fourth. So 3 then says extension equality thing. So if you have a function a, b, be a function, and you define the equivalence by saying that the outputs are the same, it wants us to prove that tilde is an equivalence relation on a. This is just extensional equality, right?
Uh, yeah, kinda. It's basically saying, okay, given an arbitrary function, uh, define an equivalence relation on the input set based on what they map on the output, right? If they have the same output, then the two elements are considered to be equivalent, even though they may not actually be equal necessarily.
Yeah, a, b can be different, but if the outputs after the function is the same, we see that they are equivalent. Um, and to me, this is just extensional equality. But here's the thing: a4 is interesting because a4 says we have an arbitrary f function and have a b, which is a partition, and it wants us to prove that the inverse of f, receiving of course b, is a partition of A. And my surprise is that we don't know anything about F. We don't know if it's surjective or injective, bijective. So how can
Well,
you
we
prove
don't.
that?
Well, we don't know anything about f on 3 either.
No, no, no. But we don't need to because we don't care if they are the same or not in this case, right? We don't know if they map. Well, they mapping them. Two elements mapping to the same thing is a good thing in this case. It's equivalence.
Um,
But in this case, we're talking about the inverse of F, which you don't even know if it exists because you don't know if F is bijective.
well, if we're assuming that the inverse is there to define the partition, then it must exist, no?
But that's the thing. I was kind of like shocked that we're not assuming anything about f at all.
Well, at the very least, we're assuming that it can be inverted, otherwise this doesn't make sense.
So are we gonna say f is bijective then?
Well, it must be, otherwise this question is nonsense.
Okay. So in that case, it wants us to prove that the inverse. Well, but if f is bijective, this is kind of easy to prove, isn't it? At least this first part. Because if f is bijective, it means that there's a one-to-one mapping between every element of A to every element of B, right? That's what bijective
Mm.
means. And they are different mappings. I should also say that. So if that's true, then this.
Actually, f is not necessarily bijective if.
That's what I'm talking
Uh,
about.
actually, let me think for a second. If b is smaller than a, um, then inverting it does not give you a function. If b is bigger than a, then f inverse is not a function either. Yeah, no, it needs to be bijective.
Yeah,
It
but
needs to be bijective.
okay. Let's recap what bijective means. It means that it's injective and surjective, right? Injective means that we are mapping every element of A to a different element on B. And surjective means that we are using all the elements on B. If we assume F is bijective, which means being both, then this, like, isn't this fairly trivial? Because my problem is that
Yes,
I couldn't
it's
say
it just
that because I didn't know shit about F. Go,
if
Tiff.
it's bijective, it just brings a partition from B to a partition to A. Yes,
Like, because here's the thing.
like
Either
the
there's a
one on one
problem
course.
and there's a gotcha here, and like we don't need to assume it's bijective, or if it
But if
is
it's not
bijective,
bijective, it doesn't have as if F is not bijective, then it cannot have an inverse.
I don't
So
know that math. I only know the one way, which is if you are bijective, it's guaranteed that you have an inverse. I don't know if the opposite is also true. That's why I'm
I
asking.
think we have proven that in an exercise, have we not?
I don't remember. It's been a month or something. Uh, I just remember the going forward. I don't remember the go all the way around. So it is true. If you have an inverse, it is guaranteed that F is bijective.
In theory, yes, and I'm almost sure we have proven that.
Marin, do you
Don't
have
remember
recollection
when.
of that?
Mm, vaguely, but I'm not sure if we actually did that.
Well, let's assume it's not. Can a function that is not bijective have an inverse? It needs to be surjective at least, because if it's not surjective, that means that we cannot map all the elements from the image that's going to become the domain, and then it's not a function. So it needs to be at least surjective. If it's not injective, then that means that mapping some elements are mapping to the same guy on the go, and then when you're trying to go back, that would be a function that maps to more than two. No, it needs to be bijective, man. Like, I think I'm doing the same exercise as Marin just did. If you try to not be surjective, you are not a function. And if you try to not be injective, the same domain, the same element of the domain is going to choose different images. Choose two different elements on the image. So it needs to be bijective to have an inverse, you see?
Mm, there is a remark in this exercise which is talking about a subset of B. Um, I guess technically we may not necessarily need to assume it is bijective if we consider only the subset, like assuming B is bigger than A, and if we only care about the subset of B,
No.
uh,
Here's the thing. It cannot be, because if we check, again, and I'm doing stressing this very much, but if we know that in order for the question to make sense, F must be bijective, B cannot be bigger than A, because that would mean that it's not surjective. And we know it's not. So if having an inverse implies being bijective, all of that hypothesis go out the window.
well, it needs to be bijective if you want the inverse to be a total function, right? If you accept a
Ah,
partial function, then you can say, okay, the inverse of f doesn't necessarily is not necessarily defined for all of B, but it is defined for enough of B such that, like, if you exclude the elements where it's undefined, then that subset. Um,
okay, that is actually the goal. Okay, you convince me. So we are saying F inverse of F, but F can be partial in this case.
Either that or it is bijective. Those are the only two possible ways to make this make sense.
Dev, do you follow?
I
What?
I don't think F could be partial here, mostly because the book has never introduced the notion
Well,
of
not
partial
f,
functions,
the
and it
inverse
has
of f.
never.
Yeah, the inverse of F
Oh,
he's talking about. Like, let's say that F is unbijective. Can you make an inverse function that is partial? Sure. right?
Then it's not necessarily a function.
Yeah, that is the problem. Then it starts the other problems of, okay, if it's a partial function, calling it a function in a math context is kind of bogus. Um, so I was pretty confused about this exercise because I was expecting this to use inverses, true, but we don't know anything about f, and I was kind of okay. But wait a moment, so because if f is bijective, the problem is solved. If f is not bijective, I don't know how to solve it then. But let's read the thing here because I kind of skipped that. If equivalence I is the equivalence relation corresponding to the partition of B, describe the equivalence relation corresponding to the partition of A. Remark. For any C, which is containing B, so it's a subset of B, the inverse, there's a typo here, right? Because there's a parenthesis here.
It's missing an open parenthesis, yes.
Yeah, the inverse on C of F, and then I have, yeah, the inverse, yeah, because C is a subset of B, so F can apply. Because we know all the elements of C are in B, which means that F, the inverse of F, if it exists, it will do something. It's equal to an element that exists in A, which is because we know that f of x is contained in C. Which is obvious, right? We know this. But this doesn't help me. This doesn't help me at all, man. Okay, but we got to a point, right? Either f is f, the inverse of s is partial, and then we don't need to talk about bijectivity, or f is bijective. Is everybody agreeing with that? And then if it is in the former, which is saying that inverse of f is partial, then it's weird because a partial function in math, what does that even mean? Are we on agreement on that?
Uh, well, yeah, I think so.
Tevo, do
I
you follow?
guess.
Okay, so I'm not tripping. This is weird. And then finally E5, which is kind of similar-ish to E true, right? Because it's now telling us that we have two distinct equivalence relations on A, E1 and E2, and then we have E3, define E3, if and only if. So like it's kind of similar in a way because this is the conjunction Marin was talking about. But this is a little different because this is using two different sets, and this one is using a single one. But that's it. Everything else is the same, isn't it? Right?
Yeah.
Like it's the same thing, but instead of two sets, it's the same. It's the same one, but we have two different equivalence relations. In which case, the by map and by applicative thought process applies.
Yeah, this is basically the set theory equivalent of that. You have to prove that you get an intersection, which is basically logical conjunction, right? On membership.
Yeah. This is essentially the same thing, but instead of a CD is a CC. Same thing. Um, okay, next one is 13. I'm gonna finish the recording now. Any comments before I finish recording?
Future people, good luck.
I mean, we can't help it. We read some stuff. We're trying to connect with the crew and stuff. Like, go figure.